So on behalf of everybody, welcome you. And so I'm Zhongren Hua from Academia Sinica, 中央研究院, and I'm the chair of this physics 5. And so first, let me introduce the juries. The one on my left is Professor Qiu Xianzhi from National Taiwan Normal University, and Professor Hu Hongyi from National Taiwan Normal University, and Professor Guo Zhelai from Academia Sinica, 中央研究院, and Professor Wang Xuming from National Sun Yat-sen University, and also from Academia Sinica, Professor Lin Gongxuan. So I think before we start, let me just state some rules. First, no internet connection is allowed, so please turn off your Wi-Fi. Okay. So if you have not downloaded your files, it's probably too late. Okay. Okay. So I think. So let's start with the agenda. Any questions? So just start, right? Okay, so where's the clock? Okay, so let's start. So opponent, please challenge the opponent. Oh, sorry. I forgot that you should introduce yourself. Okay, sorry. So reporter, please introduce your team.
So, honorable juries, fellow commenters, and most distinguished guests. We're Team Google from the Gaussian Modern Policy High School, and I'm so glad we can have a great further debate and learn from each other. Thank you.
Opponent?
Honorable judges, fellow students, we are Team NE Fresh from from a high school in Taichung, which is called the Mingdao High School. Yeah, thank you.
Thank you. So, reviewer?
Fellow debaters and distinguished guests, we're Team H105 from National Hsinchu Experimental High School. Thank you.
So the opponent, please change the report, right?
So we would like to challenge problem 14, dynamic hydrophobicity.
Reject.
Okay, so we're going to challenge problem 4 wind speed.
The second.
4
Four. Okay, now we have the problem. So presenters, please write down your name on the blackboard. And reporter, you have 5 minutes to prepare. Reporter, opponent, your next. Presenters next.
Is it necessary to wear these headphones?
Probably better.
we're ready.
Okay. So, everybody else? Agree? So we can start earlier? Okay, that's all. Start.
Honorable judges and distinguished competitors, I'm the reporter today from Team Google and I'm Neogen. So now I'm going to talk about problem number 4, wind speed. So here is the problem statement. Let an electric current flow through a coil, and when cold air flows over the coil's temperature will decrease. And all we need to do is investigate how the temperature drop depends on the wind speed, and what is the accuracy of this method of measuring the wind speed. So in my opinion of problem statement, my main focus will on first, how to measure the temperature of the coil, and the second, the coil temperature and wind speed relation. The last is thermal convection behavior. So here's my outline. First, we have observation. Second, experimental setup. We have also the experimental results, theory and discussion. The last is conclusion. So here comes the observation. How to measure the wind speed? We can use mechanical anemometry or just use a coil. And as you can see in the video, the coil's temperature is at a very high temperature when an electric current flows through a coil. And when we open the fans, you can see that the color of the coil from the red becomes to black, which means the coil's temperature has decreased and dropped. So let's moving on. Heat transfer. The coil heated by the electrical current is thermal equilibrium with the environment when the input power is equal to the heat transfer. And we know that heat loss including 3 heat loss. One is the convection, and the second is conduction. The last is radiation. When cold air flows on the coil, the thermal equilibrium will be disrupted for the heat convection piece. The temperature will drop to reach another thermal equilibrium. So here comes to my experimental setup. So the material of the coil must be not be oxidized and thermal stable. And the materials such as the first platinum and tungsten or titanium or alloys. So it is better to be not expensive and easy available. So the coil we use is the filament of the tungsten block with the glass cap removed. And the tungsten coil we use then is 60 millimeters. The diameter we use is 10 micrometers. So this is my experimental setup picture. You can see we connected the coil with a DC power supply. We also use the voltmeter to measure the voltage close and the current going through it. As you can see in the picture, we have also set a simple wind turbine, and there is a wind anemometer inside it to monitor the wind. So my question is how to measure the temperature of the coil. So we can add the thermometer on the coil, or just use traditional, just use a thermometer. But it is not necessary that we have another way to measure the temperature of the coil. So actually, the coil is a thermometer. The relationship between resistance and temperature is almost linear in the high temperature area, and which is about 100 degree K. So we can get the coil temperature from its resistance. So let's compare the resistance and the relationship with the temperature. So from the equation 2, we can get that resistance can be converted to temperature. So the relationship between the resistance and temperature is shown in the figure. But how to measure the temperature on the resistance of the coil? So in the right picture, you can see that we put the coil into cold water and change the temperature. So so we can measure the coil's. So we can get the relationship between resistance and temperature can be measured. And you can see that the equation of it is R equals 0.1960 plus 45.9. So here comes the experimental result. We have constant currents, constant voltage, and that is empirical results. So before we measure the relationship between the temperature and wind speed, the relationship between the resistance and wind speed must be measured first. Also, we have two methods of measuring this. So on the left is constant current, and on the right is the constant voltage mode. So we have 12 kinds of wind speed to measure it. And the relationship between the resistance and wind speed is shown equally. So according to question 2, resistance can be converted to temperature. And so the temperature's difference is significant in the low wind speed. The second is that in high wind speed area, constant voltage mode is more sensitive than the constant current mode. The third is the higher input powers which result in a higher initial temperature and more sensitive. So as you can see in the figure, the relationship between the temperature and the wind speed. But the relation between it is a fifth order equation, which is too complicated. So we have another way to show the relation in the line. So here comes to the theory and discussion. So the coil is heated by the electrical current. It's thermal equilibrium with environment. So as you can see in the equation 3, we have input power equals heat transfer, and including conduction, and also radiation. But the coil temperature is less than 500 degrees, so the radiation we can ignore it. Then the equation 3 can be simplified to 4. If we move the delta t to the left, on the right only remain a constant as a coefficient of the convection. So the I and B is an input power and voltage, and the AC is a coil surface area, and Tc and Tw is the temperature of the coil and air, and the H of the B is a heat transfer coefficient of convection. So here is let's compare with the experimental result. So we found that the experimental point is a downward curve and didn't pass the origin. So we suggest that the relation is a constant plus a coefficient of the convection. And for the same coil, the experimental results should be coincide with the experimental curve. So as you can see in the constant voltage mode, our theoretical term is very coincide, and in only the constant current mode, the low current high wind speed area, there is a slight deviation. So our experimental result is confirmed with our hypothesis. So we suggest that the heat convection is constant plus nth power of the speed. So here is in my problem statement I have talked about we need to measure the accuracy of this method of measuring the wind speed. So as we use the coil as an amount and the current is very simple. Just connect the coil with connect the coil with the DC power supply. Connect in series with the ammeter. So the wind speed can be obtained from the coil's current, and as we can see in the figure in the picture right, when there is low wind speed, the error of the first experimental result is only 4% error. So we have on the picture right is our four repeated measurements of the coil. So compare with the first experiment, first results, the long wind speed is 4%, and when the wind speed exceeds to 2 meters per second, the error of it is 2%. And when the wind speed exceeds to the 4 meters per second, the error will reduce 1%. So here comes to the conclusion. So first, we'll see we have the equation 5, and we suggest that the equation 5 can be simplified to equation 6 in our experimental results, this is the heat transfer coefficient of convection. The reciprocal of the filaments, filament shape has a linear relationship with the n power of the loop speed. The second is the heat transfer coefficient of convection equals a constant of the n power of the speed. The third is in low wing speed, the temperature change is significant. Hot wire anemometry is more sensitive than the mechanical anemometry. The last is higher initial temperature results in higher temperature change. Thanks for your listening.
Okay, so ready for questioning the reporter?
My question. First is, how do you measure your resistance? And
So how do I measure the resistance?
yeah.
So in the experimental setup, I say that we connect the coil with a DC power supply and measure the voltage across the coil and the current flowing through it. Yes. So I use a multimeter to measure the current and voltage.
So as you know,
Yes.
there's two ways to measure the resistance. There is an external connection method and internal connection. There's a different way to measure it.
the current.
And are you using an external connection method or internal connection method? Because the resistance of the wire will be very small.
Because because I just use the multimeter to measure the current flowing through the
And I have a question to the receiver.
Oh, time's up. So, hold on, you have 3 minutes.
opponent, please take the stage, and you have 4 minutes.
Now I'm going to look up and in the summary of reporter. In the theory, their theory is that convection and radiation will be at high times and the calculation of the equation shows that the observer data I times voltage divided by delta T will be K. And their setup is that using tangent coil and a tungsten bulb with 16 millimeters diameter and 10 micrometer. And the wind speed is used is 5.8 meters per second. And they use a multimeter to measure the current resistance and use thermal imager to measure the temperature. And the parameters is the wind speed and coil temperature. And their setup. The advantage is that they connect with the DC power supply, and the suggestion, they only use the multimeter to measure it. And we think that their theory is complete. And for the experiment and data, they show a clear relationship between it. But we have some suggestion is that you can consider more parameters. And
No? Done? Yes. Oh, alright. So, then move on to discussion.
my first question is that why a high speed wind has a non-curve rate wind speed result. Why the high speed wind has not a curve rate wind speed result.
Why the high temperature result in the
High speed.
high steam result in the high temperature result in high initial high initial temperature results in the result the more sensitive results. Oh, yes. So yes. So in the constant current mode and constant voltage mode, you can see that when the initial temperature, which means my input power is different. So when the initial temperature is 200, it will change the temperature. It's only it's about 100 Celsius degrees. So but when the higher initial temperature, like I put the input power is more, the higher initial temperature is about 500 degrees Celsius, and it will change more, and we can see the wind speed more accurately. Yes.
Oh, okay. And can you check the please 15, 16?
16.
Yeah.
Last page.
That's me. Okay.
Yes.
Oh yes.
Yes.
The power that the DC current supply is the I times V.
Yes.
And because, but I think that you should not
Ignore the radiator. Ignore the radiator.
for conduction.
because air is not good at the transfer heat,
So it means I can't, I should ignore that.
I think that you should ignore the conduction.
I should ignore the conduction. So, but in my experiment, you can see that in the equation 3, I just ignore the radiation to equation 4. So it means that if I consider the conduction, it's more accurately, and it is more accurately for the experiment. So I think don't ignore it. It's not influence the experiment. So thank you.
And I know that the resistance that the coil is very small. So
You mean why I ignore the radiation?
I mean that there's a little part dissipated in the wires to connect it.
There is a wide
The power was dissipated a little in the wire.
So you mean the temperature is?
So
You can draw it or write it down. Yes. So sorry.
I suppose that
Yes.
I
Try to be.
will not be the following because
Yes. It's equals the power. I find the power. Yeah.
but I minus
Zero.
I suppose that
Yes.
and then will be a following sequence.
So one is that's one is more.
There's a power dissipating in the wire connecting DC current supply and the coil. So I think that you should take into consideration.
Okay, sorry, I'm trying to paper. Thank you.
And I told before that, can you explain more about how you measure your resistance?
The resistance of Zook means that how I measure the yes, I use the V resistance equals the currents divided by the the voltage equals the currents times the resistance. So means what the like a line of
My question is that how do you connect the coil? Your
for
but I think that
yes.
This is called intrinsic. And what did you
Yes.
what kind of
Oh yes, I measured these two different ways of it. But in my experiment, I think what I measured point is almost similar.
so you tell it is almost similar.
Yes.
Oh.
So I think the two result is same due to the modeling. Yes. because the multimeter's resistance is very short. Yes. Like this is we use this is a multimeter and use it to measure the current. Right? Yes. So, but the different way is that when there is a current IA and this current IA, the IA will equal the current IR. But because you think that the multimeter will have a little resistance, so the multimeter will not equal the voltage. The voltage meter is voltage, so I know what it means. But in my experiment, they are similar. Yes.
And how similar is it?
How similar is it? I say that because the multimeter's resistance is short. Yes.
Back to the previous question. I think that conduction should be included because air is
I mean the conduction actually considered that. It means that so I only ignore the radiation. So in the equation 25 and the last page 26, I all consider the conduction. Yes.
So what did you think you should ignore the radiation?
Because I say because the coil's temperature we use is less than 500. We measure the coils and it's less than 500 degrees. So the radiation of the tungsten will not the radiation of the radiation part of the coil will be not influenced a lot. So
You measure how big is the radiation?
oh yes, I see that only less than 2%.
Less than 2%.
When it's the maximum is less than 2%. So maybe below 0.8%. The difference in the power.
And how do you measure the volume surface? So that there's in the radiation there's another thing called emissivity, and that is doesn't equal to 1.
Yes.
Radiation is like and you ignore this one.
So you mean this all is the radiation?
Yeah.
So I ignore all the radiation, not only ignore the not only ignore it.
Actually, sorry. So the opponent should summarize the discussion. You have 1 minute.
In our discussion, we know that the two kind of ways to measure the resistance will be very similar, so we can ignore it. And we also get that we can ignore the radiation too, because the error to this is for 2%. And set up and the report
up. So the reviewer can ask all questions.
So for the first question, I would like to first ask the report, how much do you think how much of accuracy do you think is accurate enough? Like, because you said that your result is like 4%, 2%, 1%. Do you think that's accurate enough, or do you think?
I think that's because the mechanical anemometer is not as accuracy as our wind speed coil. So I think it is more accuracy than the mechanical anemometer. So I think that is maybe enough.
Then what do you think about the same question? Do you think that, how much do you think is accurate enough?
I think their experience is pretty enough.
Okay, so then are you aware that your some of your like assumptions, or like how you do the math, like when you use the Tyler expansions, that when the x increases, your approximacy will also increase. Are you aware of that?
What's
you approximated some
Yes.
some things in. Are you aware that when the x goes up, that then your assumption, the accuracy
the
will
X goes up? What?
the wind speed.
I don't know what is the meaning of the X.
Well, like your x-axis, which in this case is the wind speed.
So I think that I didn't use the Taylor some assumption.
Okay. Then in your opinion, after you hear what his explanation, do you think that internal resistance is still need to be considered?
Because they say that the truth will be similar, but I still think that there's the difference should be considered.
Yeah. So you think that, but because they say it's under 2%, right? So you think this 2% will affect the result a lot?
A little bit, but like still think that they should consider this the external connection or internal connection.
Okay. So here, when you have the constant B, right?
Yes.
So why constant B like B? What can you explain like really quick to me why B is a constant and not a function of B?
Because I assumption is to the
Okay, time is up. So let's move on to next stage. So we have 2 minutes to prepare presentation. The connection with the switch that.
Okay, so first we'll start with the problem. So I don't think I need to repeat the problem again. But one of the big discussion in this problem is what is the accuracy of this method and how the method should go, right? So so basically the reporter, they first told us that what their setup is and how they did their experiment, and they give one good point is that they give a clear video and measurements and also clear graphs and something. But the problem with their report is that sometimes their hypothesis lack like some proof or like some more accurate explanation of why they could like maybe delete some of the functions and or anything else. And then for the reporter, they ask a lot of things about like why you could like eliminate things and how you can make this theory more complete, and then also why so mostly it's talking about why they don't have to discuss about some of the things that the reporter deleted. Okay, so and then what I want to confirm, like in the first place, of how the accuracy, do they think both of the places are accurate, is because that one of the big problems of this problem is the accuracy and the how they decide on how accurate the definition of accurate is something that the opponent is missing towards asking the reporter. For example, they did say that they were using the mechanical anemometers to like decide how the accuracy is, but then they also say that their accuracy is that they are more accurate than the ones selling on the market. But then their standard is also where their standard, they say that they're more accurate than their standard, but they didn't give an explanation of why, and that's something that the opponent didn't catch. And then for the clash part, the opponent first asked about if conduction impacts should be ignored, but like we agree with the reporter because we don't think that it's small enough for it's not small enough for us to just ignore them, and after considering it, we think that it can increase the accuracy. And then next is the internal resistance. In our opinion, one of the opponents said that it should be considered, and they say it shouldn't be. However, in our opinion, we think that the reporter should give like a accurate number or maybe a data to prove that this does not impact the theory. Okay, and then they also discuss like how high the temperature is, and then how they make the result, how can they make the result more accurate. But I think they lack they kind of lack some connection between them. And then he did the opponent, he did say that they should consider more parameters, but however they did not exactly point out like which parameters they could ask exactly, and I think that is a very okay. Thank you.
So, reporter, please conclude.
Thanks opponent and questions and good attitude for the discussion. I have some of my own opinion of the previous discussion. I will now start my concluding remarks. So the first question is, ask me do you use the internal connection method or an external connection method to measure your resistance and will be measured accurate? And in my opinion, in our experiment, the difference between the two methods of measurement is minimal. And the second question is, why does a high temperature result in more accurate spin speed? And in my opinion, there is a larger difference in temperature drop, so it will be more accurate. So the reviewer actually that why I think why the accuracy of this of the wind speed is accurate or not is as accurate as I think, right? So I think that because the mechanical anemometer is not expensive and not getting available, so I think that we use a very simple wind speed and use the coil to connect with DC power supply and to connect to the only like the magnets and also connect to the emitter. We can quickly observe that the wind speed, what is the wind speed in the environment. Yes, so thanks for listening.
Okay. Now, any questions from jury? Presenters, please stand up. Any questions? We have plenty of time.
So I have one question
Yes.
for all of you. So just imagine that you are trying to do this experiment in a different situation, like very high humidity. Okay? So is there anything you would be different in the result? How will humidity impact your accuracy of temperature measurement?
So first, can I speak first?
Yeah, sure.
Okay, so in my opinion, I think the humidity would result like in some ways, such as the conduction, how heat goes into the.
Okay, thank you. How about you, reporter?
So in my opinion, maybe it will a little bit affect the experiment, but I think it is not really affect the experiment. So maybe a little bit, but not.
Okay. Anyway, how about you?
I suppose that maybe the wind speed will affect or affect the temperature.
Other jurors? Now I have one question. Coil, can you show the slide page 15? 15 there's one with the equation that your the equation you use. So actually the question is for 3 things.
Yes.
Yeah, that one. Yeah, this equation.
Yes.
And so all of you talked about conduction, right? And frankly, I don't know what that is. Could you explain to me? So each 3 of you explain your idea about what conduction is here.
Okay.
So yeah, let's start with Rotational. Yeah.
So I think that heat loss have the three ways, right? And the first is conduction, and it is the material and the like a metal between the metal, and it will you will have the conduction heat loss. And in my question 3, I didn't ignore it. I still consider about the conduction. Yes, so I didn't.
Okay.
So how I used to like think about it when I was little was how like conduction is that when 2 solid things touch together, then heat would transfer from one to another, and that is what we call conduction.
And we think that because conduction it means that the heat transfer from coil to the air, but air is not a good as heat transfer, so we think that we should ignore it.
Okay. Thank you. So any other questions? Okay, so please sit down. So juries, you can write down the scores. Take your time. You've got plenty of time. Please give as much detail as possible so that we can pick up the winners for the international competition. Okay, so the scores are ready. So for reporter, please release your score. 6, 7, 8, 8, 5, 6. Okay, thank you. And for the reviewer, please raise your score. 5. Opponent. 5, 5, 4, 5, 4, 4. And then for the reviewer, please raise your score. 7, 7, 6, 6, 6, 6. Okay, so let's take a break. 10 minutes. Right? Okay. So the opponent, please challenge the reporter.
I would like to challenge the question number 17, hand helicopter.
We would like to reject.
And then I would like to challenge the question number 14, dynamic heat.
We will accept.
Okay. And each team, please write down the presenter's name on the blackboard. And reporter, you have 5 minutes to prepare.
So, good evening, honorable delegates and judges. Today I'm going to represent problem 14, dynamic hydrophobicity. In the outline, so we're going to first talk about problem statement and the hypothesis and the experiment and analysis, and then finally the conclusion. So for our problem statement, when a drop of liquid impacts on a horizontally moving surface, the droplet can be reflected or not, depending on the speed of the surface. And the phenomenon will be if the droplet will be reflected or not. So the main discussing point will be the speed dependent and then the relevant parameters like the height or the viscosity of the droplet. And okay, so as you can see, this is our phenomenal video, and our definition of reflect is the height of the bubble, like now, is higher than the diameter of the bubble before it contacts the surface. So in this case, this will count as a full rebound because the diameter of the height of the droplet after the contact is higher than the diameter before the contact. So this will count as a rebound. And our hypothesis. So there's going to be two forces participating in this phenomenon. First is the vertical force when it drops, and then the horizontal force applied by the circling plate. But you might think that the droplet does not have a horizontal force because it's not
moving in a horizontal way, but because it is in a relative motion, if you see it from the circling plate, it is actually moving. So when it makes contact with the circling plate, the surface energy, which is the surface tension times the contact area, will increase. When the surface energy increases, it will be in a flat form. And when it goes back to the stable state, because the cohesive force work on the surface energy, it doesn't change the surface energy, but because surface energy is the surface tension times the contact area. When contact area increases, the surface tension decreases. But when surface tension increases, the contact area decreases. So this will result in retraction, and the retraction of the molecules in water droplet, which will then become a reflex because it causes a uprising force. In our experiment setup, we use a highly efficient camera with a 871 footage per second connected to a camera to record, connected to a computer to record the footage. And then this is a DC power supplier connected to the motor, which will then make the plate to circulate. And we use a dropper to drop the droplet. The thing we use is called Teflon, which is and covered with a perfume, so it will be more hydrophobic. And experiment 1, we want to first find out which kind of liquid we should use. So we choose 3: glycerin, silicone oil, and water, which results in these two having too much cohesive force, so they will not have form change when they contact. So we decided to use water as the source of liquid. And experiment 2, we change the velocity of the vertical force and the plate, the speed of the plate. So as you can see, this is the droplets that did reflect and did not. And analysis of the water drop. The main reason of the drop is because of the change in surface energy. So the two parameters we change is velocity Vn and Vt. So we apply Weber number to two of the direction, which results in Wen equals to low Vn power to 2 and times d divided by sigma, which is the surface tension coefficient, and Wet is equals to low times Vt to the power of 2 times d divided by the surface tension coefficient. And also the d is the characteristic length of the droplet. and then because we change it, it will result in the change in Weber number of the two forces. So this is the graph of the reflected and did not reflect droplet. As you can see, this can show you the relationship of the two Weber number. And analysis. Water drop, the spread area when it makes contact with the surface is related to the vertical force of the Weber number. So we apply the theoretical result from the paper gathered from other researchers. We know when dm divided by d, the spread area divided by the characteristic length, is equal to 2 and the square root of Wen divided by 18 times 1 divided by cosine zeta. And the angle here is 123 degrees. So this is the relationship between dm divided by d and Wen. So as you can see, our data, the line on the graph is applied by this equation. And our data fits into this equation very well. So it means that our results actually fits the theoretical data from other researchers, which makes our data reliable. And the second analysis is the water drop is the extended spread area is related to the
Weber number of the horizontal circulating plate, and the extended spread area is equal to B, which is the fully flat area minus dm, and this is an estimated boundary region because, as you can see, the reflected droplets are on the right side. So we derived that the successful rebound will be in this region, and this will enclose the range of our experiment, the parameters. And analysis 2 is the water. This is the water drop in the boundary region. When we apply that B divided by dm, and all this this will come to a question of 1.148, and so these points are close to the results we gathered. Our results gathered are close enough to the theoretical data. And the third analysis is the water drop. We have to combine analysis 1 and 2, because analysis 1 is the Weber number and the relationship of it on the vertical force, and analysis 2 is about the horizontal force of the Weber number. So if we apply dimensionless XA, which is equal to spread area extension divided by drop area, so we can know the relationship of these two Weber number, and which the extended area is this minus this and then divided by the drop area, because the spread area extension is how much it extended divided by the spread area. And after calculation, you can derive at this equation, which shows the relationship between the two Weber numbers. So the water drop, and this is the dimensionless number XA we applied, and on the y-axis is the Weber number WET. So we can find out from the trend line that XA equals to 0.0086 WET, and our data all falls on the trend line that shows of it. So so we have to find out the conclusion of the boundary region. So the XA, dimensionless XA equals to 0.0086 WET as we shown, and the first analysis of the calculation is WEN equals to 18 times dm divided by d power to 2 times 1 minus cosine 123 divided by 4, and so and we use our results from our experiment, which is B divided by dm equals to 1.148, and we apply back into it, which will then show the results of it. So the blue dots are what from our results we expected that we expected it won't reflect, and in the experiment it didn't reflect, and the yellow dots are we expected that will reflect, and in experiment will also reflect. So the blue dot and the red dot is the dots that are our experimental result fulfill the theoretical data, and the green dots are the one that did not fulfill our theoretical data, which you can see here. So the slope of this WEN is equal to 0.403763 WET, which derives from the equation we shown on the previous page. This shows the relationship between the Weber number, the two Weber number. So it might not reflect because of rotation. There's an importance in the centripetal acceleration divided by the speed relevant. So if the centrifugal force is too big, it might also not reflect, and this is the result of it.
And conclusion, the reason of reflection is because of the spread and the increase of surface energy and then the back to stable state, and then it reflects because of retraction. And these liquid won't spread, and because the cohesive force is too big. And when it's more likely to reflect when the WEN divided by WET is larger. And one reflect boundary is shown here.
So the opponent can question the reporter. 2 minutes.
First, I would like to ask, how would you confirm you set the power of the velocity of circling is stable?
By using
Your equipment.
yes, this is a DC supplier. As you can see, the button can change how much voltage it applies to the.
But voltage would not be stable, right?
Yes, but it's like you.
Okay, let's skip. Okay, did you consider the air resistance while the droplet is falling?
No.
Okay, and turn to the experiment 2, please. Okay, the droplets actually have the distance, and the different distance will cause the different circling velocity, right? So do you
Cost different what?
circling velocity?
The different height cost different.
No. Rotating plate
Yes.
will cause the different circling velocity.
Of course. Yes.
So did you consider about this velocity is different?
We can control the velocity.
No. I said the radius of the droplet.
Oh yeah. You mean the radius on the plate or the radius of the droplet?
Droplet.
The radius of droplet can be controlled by the dropper if we apply the same force. Because when you apply a little bit, it becomes bigger and bigger, and then falls because of gravity.
Time is up. So opponent, you have 3 minutes to prepare your speech.
He's that wrong side.
Situation of situation.
calculated.
哎，那边开一下那个，来 switch 一下。
刚刚一直都是开。
开个这一下。
没有吧？
还没有，还要我已经。
先连因为他们那个就是清理的记载。
Oh, hello, I'm the opponent from team S501. Okay, I think I don't need to describe the problem. Okay. Okay, this is the some suggestion from us, and you didn't have the equation to involve the efficient camera and cycling effect, and your theory is lack of mathematical explanation, which you didn't quantify the experimental result, and you didn't explain why you take the reference, because the reference will have a different situation with your experiment, right? Okay, and okay, these are your strong points. Your multi-parameter is almost considered, and you have a complete calculation of the formula. Yeah. And we have some suggestion for you. Is you can quantify the experimental result next time. And you didn't explain why you use this reference in that. Yes. This formula. The physics situation will be different with your experimental situation.
We would like to move on to the discussion.
Okay, so move on, and you have John.
Okay. You said that you didn't consider the air resistance before, so you didn't consider the shape of the droplet, right?
Yes, but you said I didn't consider the air resistance, right?
Yeah.
But because it is actually very low when we drop the droplet, the air resistance won't affect much of the result.
How to quantify the air resistance is really small.
Because as you can see from our video, you can see that the shape of the droplet, the droplet.
Okay, I said, how do you quantify it?
Quantify the shape of the droplet.
No. Quantify the affection of the air resistance.
We won't quantify that because
Okay. This way. Okay. The droplet will drop into the different distance of the plate, right?
No, we control the radius of the plate we drop because we can make the dropper stay in one place.
Okay. So back to the question before. Can you compare the situation and the reference?
Yes, as you can see, as suggested from the name of the report, the formation and dynamics of a blob on free and wall sheet induced by a drop impact on the surfaces.
So you are sure that their experimental material is same as yours?
In this equation, it didn't involve with the material. In this report, it uses water as the fluid, and as you can see, it considers dm and d. dm is the extended area, and d and D is the characteristic length.
Okay. And next question. Do you consider, because the droplet has a diameter, right?
Yeah.
Okay. The different diameter will cause the, because you know the airflow is a wave, right?
Yeah.
Okay. The airflow will have the crest and trough, you know? Okay. The crest and trough will impact the reflection of the droplet.
Oh, you mean when the rotation is in a high speed that creates a airborne area where it floats up the droplet?
Yes, and the airborne will create air wave, and
Yes, that's in the case where the circling plate is in a very high speed.
so my question is, do you consider the crest and the trough of the air wave?
No, since we use, as you suggested before, that you say the voltage will differ when time passes, but this is a direct voltage. And
Can I use the blackboard? Please.
Yeah, please turn on the light.
yeah, you mean that there's a area.
Yeah.
Yeah, because we don't have this because the circular plate is not fast enough. That's when you can feel it around it, but it's not strong enough to affect the size of the droplet.
Okay, let's discuss the distance between the droplet and the plate. This will have a distance, right?
Yeah.
And the distance will cause the, because this is a wave, and the crest is this and trough is this. And the crest and trough will impact the droplet shape. And do you consider the trough and the crest of the airflow will impact the shape of the droplet?
No, because we dropped it at a pretty low. It's 12 centimeters. It starts from 0.5 centimeters and then 2 centimeters. So as you know that this distance is very short, so this will not affect, and we did not consider it inside.
But the force of the air resistance will impact the contact area of the droplet and the plate, right?
The contact area, do you mean by spread area or the extended spread area?
Okay, I will skip this question. Okay, there is a highest point and the lowest point, right? And the lowest point will be the less velocity, and the highest will be more, right? Because of the air resistance. So do you consider the, okay, oh, it is opposed, sorry. This is less speed and this is more speed. So do you analyze the subsequent mass of the droplet?
Maybe different, like
Different motion.
distribution.
Different function of the motion. Motion of like this or this or this.
So you're saying that these different parts will have different motion?
Yeah.
No, because we consider the cohesive force is strong enough to centrify the droplet.
Okay, so back to the forward question. How do you quantify the cohesive force is big enough to support this shape of droplet?
Do you mean that how do I consider it is strong enough?
Yeah.
From our experiment, because we can, as we drop the droplet, we can see that it forms in a circle, but not like when you drop it water, it's dropped as a circle, not as a splash or. Yeah.
But
that's the demonstration of
but
big
that,
enough.
that was just your C. You didn't analyze the whole shape, right?
Yes, because what we see is how the droplet change after the contact. We're seeing the reflection of it, the retraction of it.
So you say, can you repeat the reaction one more time? Answer of this question.
What we want to see is from the problem statement is it may be reflected or not. Then because we want to see is what after contact, when anything drop on the surface, it goes first to this, then reflection.
Yes.
So this takes a relevant time. So the air resistance will not be affecting the motion after the contact.
So your theory is to consider the recover of the okay. But the contacting area will impact the force of the yeah. So the bigger area, bigger contact area is the force may be the smaller. So it might impact your result of experiment.
You mean like because the contact area will affect the surface energy?
Yeah.
But the surface energy will then change back to cohesive force, no matter like how much of it. And as we can and this is the final goal of our experiment. We show you the boundary region that which
Okay, stop. Sorry. Okay, can you explain the surface energy?
the surface energy equals to surface tension times contact area.
How do you define it meaning? Physical meaning.
The relationship between I can't memorize.
Okay. Do you consider the dynamic viscosity?
Yes. That's why we did not choose glycerin and silicone oil as our liquid because it has the viscosity is too high. It will have a too strong.
What do you mean too high viscosity?
So when you use glycerin, when it drops, it forms in a shape like that. When it contacts, it's still in a shape like this. It doesn't change the shape.
That is what you see, but actually would not be the same as.
Yeah, but if it stays the same, there's not going to be a retraction of it. That's not what we want to see.
Okay. Do you consider the curvature at the bottom of the droplet? The droplet.
No, because the curvature of it forms in a circle, like a circle. So the curvature of the circle, like is the same.
You make like a circle, but you didn't consider air resistance, so you still insert that the shape is circle.
Yes, so we were taking that consideration.
Okay, time is up, so let's move on. The opponent should summarize the question. You have 1 minute.
Okay, their theory is completely good, and the result of their experiment still haven't quantified yet. And the other big question is that they didn't consider the air resistance, which will impact the shape of the contact plate and the droplet. And they consider many parameters. These are the this is the advantage.
So the reviewer, you may start to ask questions. You have 3 minutes.
Thanks, the report perfect presentation and the opponent's good questions. So I'm Daniel Jun from Team Google, so I'm going to review the problem number 14, dynamic chemical resistance. So the first question I would like to ask is, could you explain the reason of using circular plates?
Because
Yes.
it's the problem statement states that we want to see the moving surface,
Yes.
and if you can more precisely control the velocity of it by making the same radius of the circling plate and using a DC.
I understand. So what's your opinion on why the reason of using the circular plates?
Because I think they're just drop the droplet into the plate, and the plate will still circulate, and the plate will actually can simulate to infinity big plate.
Okay, I understand. So the second question is, how could you define the surface energy?
The surface.
Yes.
We define it as the contact area times the surface tension, the surface tension of the liquid.
Okay. So, and what is your opinion? Could you why define the surface energy?
I think the surface energy will provide the droplet the recover force to become the stable.
Provide the recovery support.
Yeah.
So, I want to ask to see in your report on the conclusion. Yes. So in the conclusion, you mentioned that what I want to know is what is the WET and what is the WEN.
It's the Weber number.
Yes. What is WET and WEN?
It's the Weber number of the two forces.
The Weber number is supported.
Yes.
Okay, so.
The WEN is the vertical force and WET is the horizontal force.
Oh, that's it. So the last question I would like to ask is, how do you ensure that every time you drop a liquid with the same with the same value in the water?
So actually it's like a pipette. So there's a precise volume of it when you drop it.
So can you please turn to equation 1?
Here, you can see this is the needle of the pipette.
Okay,
But
time
the
is up.
difference,
Time is up. Let's move on. So reviewer will have 2 minutes to prepare your speech.
switch 过去了。switch 过去了，是 reviewer。
I'll start.
Okay, you have 4 minutes.
So, honorable judges, distinguished competitors, I'm the real Neil from Team Google, and this is the problem number 14, dynamic hydrophobicity. The reporter has mentioned, the reporter and the opponent has discussed about the problem statement, so I won't talk about this. So here comes the summary and comment of the report. So the phenomenon in the report is that a drop of liquid reflects back after colliding with the dynamic surface and loss applies of cohesive force. And the changing factor on the reporter is different liquids, and the second is the velocity of the plates and also the velocity of the droplet. And the setup is a DC power supply and a circular plate, water, motor, and camera, and droplet, and also a computer. And the conclusion of the reporter's experiment is that if cohesive force is too big, it won't spread. And if WET and EN is larger, then it is more likely to reflect. So I have some advantages to the reporter is good presentation and many graphs, comparison between the theoretical and experimental data. And the last is many parameters considered. And the suggestions for the some graph should have the units and unclear definition to some symbols in the formula. So here comes the summary and comment of the opponent. So in the opponent, I have also have an advantage and suggestion for you. So I have a clear many points in the experiment and also ask many specific points. Consider many details in the experiment. But some you can do more better, so maybe more focus can be put on the experiment data done by the reporter. So here comes the summary and discussion between the reporter and the opponent. So the opponent has asked that, did you consider the effect of air resistance on the droplet and also quantified it? And the reporter said no, but in my opinion, I think that air resistance may be hard to quantify. But the reporter can consider the effect air resistance has on the droplet, just like the shape of the change. The second question is, did you consider the effect of the air wave on the droplets? And the reporter's answer that no, because the distance is very short, so yes. The third question is, how are you sure that the cohesive force is enough to support the droplets? And the reporter asked, this can be observed in the experiment. I also agree with the reporter. So here comes the conclusions. I think the reporter has some mispoint is that there is a good theory for this problem, but some effects of such as the air resistance are not considered in the presentation. So my question for the reporter and the opponent is can you explain the reason of using a circular plate? The reporter answered me that you can more precisely control the velocity of the surface. The opponent also answered me that the plates can be similar to an infinity big plate. And in this question, I agree with the reporter. So my second question is, how did you define the surface energy? The opponent answered me that the surface energy will provide the droplets recover force. Yes. So thank you for listening.
Thank you. So let's move on to the next stage. Recorder and conclusion. You can wait until we will start.
So the concluding remarks. The major questions asked is, didn't consider the air resistance, but we believe that that doesn't matter the rebound situation when the droplet was being dropped off at a short distance because it is a time difference, and we will also consider that next time in our experiment. And is the reference reliable? Yes, it suits the experiment. And did you consider the curvature or the change of form of the water during the drop? No, because we want to see what happened after. And some improvements of the discussion is that we can discuss more about the data and the results of our experiment. So thanks for the effort. So thank you.
Okay. So we are quick. So we got plenty of time for your last questions. Any questions?
You are the expert.
No.
Okay, I have a quick question. What is the material of this?
Over this.
Yeah.
So the material of this is paraffin, which is highly it's the most hydrophobic material that we can get from our lab because it's more suitable for us to see the retraction.
Any other questions?
One question for the reporter. So, can you please use one or two sentences to explain in your experiment how do you control Vn?
The Vn is the height of the because it is the speed of the vertical force. So if we make we can make sure the height of the dropper. So there's different height when we drop the dropper.
Questions? Now I'll ask a question. So I want to ask three of you. So before please show the slide with having the wave number.
With the Weber number?
Yeah, wave number. So the Weber number, as far as I know, it's a fluid, it's a dimensionless parameter in fluid dynamics.
Yeah.
And so I want to know the physical meaning of the Weber number and why did you use it? And for the other two teams, and I want to ask you whether if you can explain what the Weber number is, if you know. If you don't know, just say you don't know. And whether if you agree with the reporter, whether you should use this is appropriate dimensionless number to use.
So as you can see, the Weber number is how it how the force of it can be affected to the retraction of the fluid. So if we consider the Weber number, we can precisely know better about our parameters and the relationship because we can apply it to the calculation.
So opponent.
Okay. I think the Weber number, it's like the parameters like the Reynolds index, Reynolds number. Is to the physical meaning is to quantify the fluid is turbulent or not.
Let me rephrase. You don't have to defend him, right?
Yeah.
I just want to ask your opinion.
No.
Okay.
I
You
just
like that, right?
Yeah.
Okay.
So I think you can see the rule for nothing as an equation of the particle. Actually, I'm not quite sure of the physics meaning of this. So yes.
Okay. Okay. Thank you.
So, any other questions?
I have one question for the reporter. Can you explain the definition of the surface energy in your
Surface energy.
Yeah, how do you define the surface energy?
Surface energy is the product of the tension, the surface tension, and so if as the surface energy increases, there's less surface tension of the droplet, so it's going to be a the spread of the drop. And it does not provide the force to create retraction because
It's a force.
no, it's not force. It's an energy. The force applied to make the retraction is from the cohesive force of
So,
Go ahead.
very final question. So, yes, no question to all three teams. So here we have three figures. If we start from figure 2 in the middle, the energy from Earth static heat and this start to rotate, will we have a case similar to the bottom figure? Yes or no?
Sorry, I don't comprehend.
So here, instead of dropping a drop, we just start from a drop sitting on the plate.
So the plate is not rotating.
It's not rotating initially, and then we start to rotate. So it won't.
Oh, no.
No. Okay. Then how about we review it?
You mean the circle? I think yes,
No.
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 Do I have to get the explanation?
No. It's a yes no question.
Oh, no.
No.
Okay, time stop. So the jury's back on the floor. Take your time. Okay, the scores are ready. So for the reporter, please raise your score. 4, 5, 5, 7, 6, 6. Okay. So for the reviewer, please raise your opponent. What? Okay, I'm low on sugar. So for the opponent, please raise your score. 4, 6, 4, 7, 5, 5. And for the reviewer, please raise your score. 7, 7, 5, 8, 6, 6. Okay, so到了吗？可以吗？ So let's start final round of the day. So the opponent, you can challenge the reporter for the problem.
I would like to challenge rebounding capsule.
Rebounding capsule. Number, our number.
15.
Number 15. That's that? Not yet. Okay. Okay, you have 28 seconds. We're set. So we have problem number 15. Okay. So please write down your presenter's name on the blackboard. Reporter, please take the stage.
Okay. I'm going to present the question 15 regarding capsule. So that the problem is a spherical ball dropped onto a hard surface will never rebound to the release height, even if it has an initial speed. However, a capsule-shaped object like a tic-tac on the other hand, may exceed the initial height. Investigate this phenomenon. So our experiment method is that we drop a capsule-shaped pill from a certain height while capturing the spinning status with a high-speed photography. And different air resistance, height, and releasing angle will influence the angle when the object drops onto the surface. Thus, we investigate the phenomenon without considering air resistance. Next is our observation. You can see that the pill dropping onto the surface actually rebound higher than the second contacts the surface at the second time. So to calculate the contact angle and the velocity, we consider the whole pill on a 2D Cartesian coordinate system. So we have x, which can be positive or negative depending on the angle of the inclination, but inclination phi, but y remains positive regardless. As phi is varied, the magnitude of x passes through a maximum value of a minus b at phi typically about 38 degrees, depending on the ratio of a to b. Consequently, the torque on the ball due to the normal reaction force is a maximum when phi is about 38 degrees and 142 degrees. The center of mass of the pill is incident from left to right with velocity components Vx1 and Vy1, and rebound with the velocity components Vx2 and Vy2. Just prior to the impact, the vertical speed Vpy1 is given by Vy1 and x omega 1, which x omega 1 is r omega sine theta in the last picture. So we also have the rebound velocity Vpy2 and Vpx2. However, x and y are not actually the same immediately before and after the impact, since the ball rotates during the impact when it bounces onto the surface. Next, due to our experiment videos and analysis and research on papers, we consider the angular velocity to be 10 to 20 radius per second, and a 15 millisecond impact duration, which tells us the object typically rotates 10 degrees to 20 degrees during the touch. Then we explain how angular velocity and angle impact the height of the object. So we can see, according to Newton's second law of motion, we have equation 1 and equation 2. Well, considering the torque, we get equation 3, which in the present experiment, the ball always gripped the surface during the bounce. Therefore, a simple relation between F and N did not exist. We assume a spin parameter S2 as y times omega 2 divided by Vx2. If S2 equals to 1, the object comes to rest on the surface and after the bounce. However, if S2 is smaller than 1, in the second example, the object would slide forward, and the object would slide backwards if S2 is bigger than 1. So we have that the later condition is described as an overspinning mode, which the sliding friction acts to accelerate the ball in the horizontal direction. Overspinning can arise if the ball grips the surface during the bounce, then loses its grip and starts sliding backwards on the surface due to the release of elastic energy stored as a result of tangential distortion of the pill or the surface. We then substitute omega 2 in equation 3, which yields the solution equation 4, which tells us 3 important parameters that should be considered in the whole experiment, which is the incident ball spin, omega 1, initial horizontal speed, Vx1, and the inclination of the ball, xy. where we have I0 equals to S2 ICM plus my squared. As for a spherical ball, there is no simple analytical relation to determine By1. There's By2, but the ratio By2 divided by By1 in our experiment can be measured. Similarly, there is no simple analytical relation that can be used to determine S2, but S2 can be measured as well. This is why a spherical ball never rebounds to its initial height. So, S2 actually varies typically about from 0.8 to 1.2 depending on the 3 parameters above. And for example, we have that if we have S2 equals to 1 provides a good description of the bounds of a pill. Drop vertically without spin, that Vx1 equals to 0 and omega 1 equals to 0. Next, we can see that with the friction, these are the parameters that I imagine there will be. And the 4 above highlighted were considered in this experiment. This is the picture that we put the video into Chapter, and we can see that the second time actually bounced higher than the first time. This is the angle that we consider here. The image isn't clear enough, but we have we did many experiments and take the average of them. So for experiments for sandpapers, both smooth and rough sandpapers group between the pill is too big, so that the friction can accelerate the ball but actually drags it down, so it can rebound. As for the table, the release angles 30 to 75 degrees. When it contacts at an angle of 30 to 45 degrees, usually have the overspinning mode, which we can see that no matter clockwise or counterclockwise doesn't impact if the overspinning mode exists. So for conclusion, for the theory part, the semi-major axis of the pill is A equals to 5 millimeters equals to 2 feet. And for our first conclusion is that the result when phi is around 26.6 degrees, X has its maximum. The next is that the spinning potential energy is stored and released when contact the surface at a certain angle, and used to bounce vertically. Next is that overspinning mode is one of the most important thing that stores extra energy to the object, which what we see from the Newton law of motion. Second Newton law of motion, we have 3 important parameters, which is omega, Vx1, and the inclination. And for these, for the ratio and S2 cannot be considered by theory because the spinning change, the pill change its inclination when it touches the surface during the contact. So we can only measure it experimentally. Next is that in the experiment we see that at a contact angle around 30 to 45 degrees has the best probability to reach its initial height, no matter clockwise or counterclockwise. And we see that a faster initial angular velocity, omega, can also increase the probability which overspinning mode it can be seen. And thank you for listening.
Okay, time for question from the opponent.
Okay, honorable judges and fellow contestants, I'm the opponent from Team Google. And thank you for your hard work and your good presentation. And so the first short question I'd like to ask is, what is the shape that you used in your observation video?
Oval shaped pill.
Oh, so it's an oval shaped pill. Do you think an oval shaped pill is similar to a capsule shape, like stated in the problem statement?
We chose the capsule shaped pill because it's similar to the problem statement the Typt made.
Okay, thank you. And another question is on page 10. Okay, so here you mentioned sliding and also sliding backwards. Can you show what this means, maybe on the blackboard?
So we have the Vx2, which is going forward for the pill, and y omega 2, which goes backwards, which decrease its make it move backwards. So when it slides backwards, y omega 2 is bigger than Vx2, which the pill is actually still moving forward, but the contact point is sliding backwards. And then it suddenly stops and grip the surface and keep on moving.
Okay, so the contact point is sliding, and after
A time,
it will grip the
the surface and then move on.
Okay, thank you. And thank you.
Okay, time is up, so let's move on. The opponent has 3 minutes to prepare.
Okay, I'm the opponent for problem number 15, rebounding capsule. And here is the problem statement. So in this presentation, the main focus was using a capsule-shaped object similar to a Tic Tac mint, and also investigating the phenomenon that it will exceed its initial height. And here's the outline and summary of the reporter's presentation. So the phenomenon is that a capsule-shaped object may rebound back and exceed the initial height. And also there are some laws apply. And here is this and the setup. The reporter used an oval-shaped object that is relatable to a Tic Tac mint. And also parameters are the contact angle and also the drop angle, and also and for the results, for a spherical ball, there is no simple mathematical relation to determine how it will move. And some advantages, there was a good presentation. There was a lot of theory to back up. There was a lot of theory to back up his experiment, and also a clear graph. And some suggestions are maybe the reporter can add more experiment footage. Okay, and here is my questions for discussion. So here is some questions for the theory. So how does the reporter think the motion would, what the motion would become if there was no friction force? And also, what is the main reason that causes the capsule to bounce higher than the initial height? And also, the definition of sliding friction. And also, I want to understand more about elastic energy since it was mentioned in the presentation. And next is the setup. Did the reporter measure the horizontal contact velocity, maybe using tracker, and for the experiment, how did the reporter measure the contact angle when it contacts the surface, and also how did the reporter conduct his experiment? How did he drop his capsule? And for the conclusion, what does the reporter mean by semi-major axis in page 19? And also, what is decay in page 19? And thank you.
We can start the discussion.
My discussion. So first, let's start off from the conclusion. So can you explain to me what a semi-major axis is?
Oh, it is. I didn't actually know that in English, so I Googled it. But this is what it means by semi-major.
Okay, so for
this is A and this is B.
Oh, so this is for the oval shape.
Yeah.
And also on, can you explain what decay is?
Oh, it's just any like 1, 2, 3, 4. Because 180 degrees didn't impact the result.
Okay, so K seems to be a random number.
Yes.
And also the phi here, can you remind me about what it means?
It's the inclination when it contacts the surface.
So when the oval contacts the surface.
Yes.
Okay, so, thank you. And also another thing I would like to ask is about page 15, where we have the chart. Yeah, this graph. So what point did you track in
the CM of the center of mass of the pill, and I track it each and every frame. Check it by each and every frame.
And how many frames per second did your camera shoot at?
I actually don't know, but I think it's clear enough to show there's a bounce higher. There's bounce higher.
Sorry. The two heights here seem to be about the same.
Yeah, but for a spherical ball, the problem there says that the spherical never reached its initial height. This is only one of our experiments, like it's close to the same height. But in the observation video which I put in the first place, actually shows there's a really big difference between the first bounce and the second.
Sorry, so in your tracker data, was the experiment done with a spherical shaped object, or was it with the
It's just oval. We only did it for this oval object because the problem already stated that a spherical never bounces.
And did you track the motion for your observation video? Because it seems to be in the common statement. So did you show a graph that the second bounce is higher than the initial? Did you track your?
Oh, this one?
Yeah.
Did I track it? Oh, yes. But I chose the one that it's like the same is because it's just to say that it can reach its initial height. I just randomly pick one that the overspinning mode is seen.
So in one of your conclusions, you have a graph with the horizontal angle and also the yes. To the table. Yeah, this one. So here you have a release angle and also contact angle and angular velocity. Okay, so for the release angle, how did you control and measure this angle?
I put a board which I measured under a clip which is put on the side of the table and measure the angle and put it on it so that, and when I put it on it, I measure it again so that when I release the clip, it won't, it will be like actually 30 degrees or 45 degrees. But the 0.0 is not what we measured, it's just we think that it's close to.
Oh, okay, so the difference isn't too big.
Yeah.
Okay. And how did you release your oval shaped object?
We put it on a clip which is put on the, which is stick to the side of the table.
And you just let go of the clip?
Yeah, let go of the clip. So there's no contact in between my hand.
Oh. And when this oval shaped object is dropping, will there be an angular velocity?
That is when there's no air resistance, there will be no angular velocity if I drop it vertically. So that's why I said that we didn't consider air resistance in the first place. So if we don't want the air resistance to impact the result, we can, for the first one, we can track it when it contacts the surface. Second, we can just give, if we have a better experiment set up, then we can just give it a initial speed and contact the table at a very small distance. So there will be no angular velocity that the air gives it.
And also in the last column, what is the angular velocity that you're talking about? Is it the?
I mean when it's spinning, if it's spinning like clockwise, means it's at this place and it's spinning like this, and when it contacts, it's spinning like this. But we did that is before the contact, but not after the contact.
Okay, so this angular velocity is before
the contact. It's spinning clockwise.
And is this angular velocity, does it make a big difference to your experiment?
We didn't consider the parameter by calculating different angular velocity which impacts. But when we compare different images, we can see that by eyes, of course, when it spins faster and there's more image in when it spins a bigger angle in each and one frame, then it has a faster angular velocity. And in that case, there's more overspinning mode which we can capture.
Okay, because at first I asked, you didn't consider air resistance, right?
Yeah.
So it shouldn't be spinning when it's dropped.
Oh, it after the first contact with the table gives it an force, which gives it the.
Sorry, that's so this angular velocity is when you're releasing.
So in my like in my observation, the first time when it drops onto the surface, there's no overspinning mode.
Okay.
But in the when it has the angular velocity and drops onto the table for a second time, we see the. So for the first time, it contacts the table. There's nothing happen. But the second time, when there's an angular velocity, it bounces higher than the first time.
Okay, so in your last column, is that angular velocity the same for all the?
Oh, I just said that we didn't consider if it's the same, but we see if the angle in each and one frame is bigger, means that the angular velocity is bigger. And in this case, most of our overspinning mode video can see similar places that the angular velocity is bigger than the one that didn't happen.
Okay. And another thing I'm curious about is the contact angle. Since the release angle is all different, why is the contact angle so similar?
In my point of view, I think that it's because the different contact angle gives the force it gives different, and the grip might be different too. So the spinning I just said might be 10 to 20 degrees when it contacts the table. So there might be a difference that the surface gives. There might be a different force that the surface gives our pill. So and in the actual experiment, there is air resistance. So this is when we see in tracker, it's the frame says that it's around 30 to 45 degrees, but not what in our theory count there's 30 to 45 degrees.
Thank you. And also, I think you mentioned elastic energy.
Yeah.
Can you turn that? So I'll ask my question first. How does this elastic energy affect the phenomenon?
So, in a very simple, imagine if the pill is spinning very fast, and like in my video, if it bounces onto the surface and stops spinning, the energy which is used to be spin is used to be bounced, right? Can you imagine that? So if the spinning energy is used to be bounced, and if the contact didn't lose any heat or any energy, then the energy is used to be bounced vertically.
And also another main question is, can you quickly explain what is the main reason that that allows the capsule to exceed its initial height?
So as I said, at first the spinning the contact might make the energy stored into the spinning, and then released at the second contact. So, and the second one is that when we contact the surface and there's overspinning mode, the sliding friction forwards might actually accelerate the ball and give it more energy than I release it.
Okay, so the main reason is because of overspinning and also the energy stored inside of it.
The energy stored to be spin at the first bounce.
Okay, time is up. So the opponent will summarize the discussion.
Okay, so I'm going to summarize my discussion with the opponent. So the main reason that the capsule rebounds back, that it exceeds its initial height is because of overspinning mode and also the energy stored in the rotation, in the spinning. And also, I think there was some conflict between the theory and also some of the experiment, which is at the part where he mentioned air resistance. And also, I think that the reporter can do more experiments and also analyze more experiment data to make his presentation
more complete. Okay, you have 2 minutes to prepare.
Shouldn't we ask questions?
Yeah, sorry. Missed the laptop. So 3 minutes to question both
Thank you
sides.
for the good presentation and quick presentation and a good discussion. So, in the overspinning mode, are there any energy loss, or is it in the elastic collision or in inelastic collision?
Of course, in a realistic world, there will be, but in theory, we didn't consider it. But the result we have is we didn't consider the spinning track, but the contact with the surface is what we experience, what we make a conclusion on.
What do you think?
On overspinning.
Yeah.
In experiment, there will definitely be energy loss, and I think it is an inelastic collision.
Do you think there are any angular kinetic energy being lost or transferred to other form of energy during the collision?
Of course, there will be like heat or other, like a loss of its mass when it contacts or spin, but we consider the whole theory without these small effects, which in my imagination, this don't impact the whole, the little loss of the mass didn't impact the result for the a more large mass of the pill.
So there are no energy transformation.
There will, of course there will be, but we didn't consider it because we think it can be ignored.
So I think the angular, you said angular kinetic energy. There will be some energy loss in physics in reality, and also some of it can be changed into potential energy or also kinetic energy.
So you didn't consider the change of form of the contact points when it drops on, because it can become, the contact point can become a flat through drop. Will it affect your results?
In my imagination, it don't impact the whole theory because the theory didn't tells us that the change of the contact point. It's just the force that the surface gives.
Can you quantify the sliding of the contact point?
No, I just said that the force and all the things that the surface gives will change during the whole thing. It's like a decrease because it's rotate when it
Do you agree on it?
Can you repeat the question?
The contact point sliding, can you quantify it, and it does not affect it? Do you agree?
It might affect the inelastic collision.
Reviewer, we have 2 minutes to prepare your speech.
thanks for the favorable discussion being done. Okay. So the problem statement, I will not go into this again since they already done this. So the overview of the reporter. The advantage of the reporter is that a clear presentation of the phenomenon through the video and existing states and detailed explanation of the theory. And they considered many parameters during their experiment, and a clear conclusion was made. However, the suggestions are can focus on the parameters that might be more relevant, and there is a lack of the explanation of experimental setup and figures during the presentation. And I believe that there's a lack of data, and they can provide more data to see more relationship between it. And the calculation can be done more clearly, so we can understand more, and they can consider real life situations that considers friction force and other forces. An overview of the opponent. So they ask important questions and catch us on good. And major discussions. Discussion 1 is the shape of the object. So opponent asks, what is the shape? Why do we choose it, and does it differ from capsule shape? And the reporter said it is an oval shape and it is similar to capsule. And in our opinion, however, there's a difference between an oval shape and a capsule. So we believe that the results will differ, and we cited on the opponent's side. And discussion 2. Opponent asked, why did you choose to present a graph that doesn't show a great difference? So the reverse said, we wanted to show that it can reach the initial height. But we believe that a graph showing a larger difference will be better to demonstrate the phenomenon. And they said they're randomly choosing data. How did you release the capsule? Well, we release it by using a clip. So we believe that a better presentation of the experimental setup with the diagrams can make us know this better. The discussion 4 is, how does this the elastic energy affect the phenomenon? So if the pill is spinning very fast if it bounces on the table, the spinning energy transfers to bouncing energy, and we agree with the reporter. So conclusion, this is a very good discussion overall, and a lot of major questions were discussed, and we understand this phenomenon better. And yeah, thanks for the participation and good night.
Okay, so the report
So for the opponent and the reviewer, they're like suggesting that there should be more experimental data. So I agree with that. But in our randomly choose data, we show it on the PowerPoint, can actually tell us about the same thing. And if the reviewer said that we choose the image that only reach its initial height but not more, because I think we already have a clear video that tells everyone that it can bounce like 3 times or 4 times higher. Then is our concluding remarks that the opponent mostly asked about details of our experiment, like how the clip is set up, and we understand that we can have more images and pictures on there, but to make it more reliable. So, however, the considered more real-life conditions can be a little more complicated, but we still agree with that. Next, the oval-shaped capsule is, we chose that because the shape is similar to Typt mint. And Typt mint isn't actually an oval shape, but in the problem statement it tells us that it can work, so we chose it as our setup. And how to release and control the releasing angle is using a clip, of course. only convert it into elastic energy. Yes, there will be, but we didn't consider it because it's really small to the impact. And next, will the contact point sliding affect the result? Can you quantify it? The force which the surface gives is more important, which we didn't quantify it, but think it can be ignored. Suggestions to the opponent is that we think that more discussion on the experimental data instead of the experimental way will be better.
So it's time for jury's question. Any
So,
question?
one question for the reporter. What is the material used for the oval-shaped object? For this oval-shaped object, what is the material?
We didn't consider the material, but it's just different kinds of medical ingredients. Because as for a tick timing, we imagine that if they consider a tick timing,
Okay, so if you don't know what is made of, it just appears.
well, we know, but we didn't consider it.
So if we use a different material like a rock, a very harsh material, will the result be any different? Yes or no?
Yes, there will be different.
How about the reviewer?
Yes, there will be difference.
Thank you.
Any other questions?
Okay, my time focus. So I asked, can you show the movie, the only movie that you present?
Yeah.
And I have a question for three of you. First, I guess you all think rotational energy, I mean the kinetic energy of rotation is important, right?
Yeah.
And so by just, if you are given this movie, say it's kind enough for the reporter to give you the other two teams to this movie, how, just quick answer, how would you measure the rotational energy?
So do I have to?
Yeah. So you can answer.
How do we measure the rotation of the energy?
Yeah, the kinetic energy of rotation.
We only consider the spinning speed, the angular velocity, but we didn't calculate the actual number for its energy.
Okay. I didn't see, I don't see you present the data, right? Did you calculate the rotational?
I calculate the speed of its angular velocity, which I said that we collect each and every frame and see the inclination, because every frame is the same time duration. So if in this time duration, the inclination, the angle change more means its angular velocity changed more. But we didn't use this angular velocity to make a more experiment into the phenomenon of the energy, the spinning energy.
Yeah, so for the other, so how would you measure the energy of rotation?
Okay, so I'll answer first. So for calculating the rotational energy, I would calculate the moment of inertia for the pill and also the angular velocity, maybe using tracker.
We'll also use a tracker to calculate the angular kinetic energy and the kinetic energy after the contact, because we believe that the bounce of the capsule is resulted from the transformation of energy.
Okay.
Can I add more?
Yeah.
And one of the important things that we didn't measure it because we did it in a reality, world, that maybe there's a mass loss and maybe there's a shape difference. So we think that if we calculate only the angular velocity, there may be too many parameters to change the energy, which if we count that there's 10 times more energy is given, but maybe it's 20 more because it lost 10 times of its energy already. Yeah.
a short question for all of you. Right? The issue is how many times you have to collect the data. So in your opinion, okay, how many times is enough?
Yeah.
Yeah, so can you just repeat the, say the number you think is sufficient? Right?
Calculate how many times?
Yeah, how many times you have to, for all of you?
Oh, and let me answer first. So for this,
No, just a number. We are running out of time. How many times do you think is enough?
it's like more than 100 because there's
Okay.
20%.
How about you? How many times?
I believe 3 to 5 trials.
3 to 5?
Maybe 100 to 200.
Okay.
Okay, thank you. This is very clever question. Okay, so I think it's time for jury to judge. Okay, let's go. Sit down. Take your time to give the score. Okay, the jury is ready to give the score. So for the reporter, please raise your score. 5, 5, 6, 6, 4, 5. For the opponent, please raise your score. 7, 7, 6, 7, 5, 5. For the reviewer, please raise your score. 6, 7, 5, 6, 6, 7. Okay, so I want to ask juries whether you have a general comment or praises or. Okay.
I think for the 3 rounds, the score of opponent is relatively low. Here, I want to comment how to raise your score, especially for opponent and reviewer. I think if you want to ask questions here, there's we have the comment to evaluate form that you need to have your own opinion. This is very important. So when you ask question, maybe you can describe more why this question is very important and continue to discuss with your, for example, reporter. So why you want to ask this question? Not just ask question. You will have your you will not have your own opinion, and the score will not be high. So this is a general comment for asking questions. Yeah, especially for opponent and reviewer.
Follow up, right? So let's asking a question. My comment is answer the question. I intentionally ask a very, the question that the answer should be simple, right? So, it's also, it works better you give precise answer. Right? Lengthy answer doesn't help, only confuse your audience. And you may not need to rush to answer if it takes a few seconds to think. Take your time, right? Yeah, and I can see, I think that the first round, everyone was warming up. I trust you'll do better tomorrow. We are also doing the same.
Yeah. Any other comments? I have two comments.
So the let me begin with some prep. So all of you are doing great. So for all of you, for different teams, you have different strengths, so you can think about and learn from other teams as well. And so I want to emphasize two things. So this is about physics, and another important part is about communications. So I know it's time, there's time constraint, but for some of the time, so it's very normal, we'll feel nervous. However, for some of the time when some of you ask questions, you actually didn't listen too much from other answers, and then follow up the questions. So that's something you can practice, and then you get to better. Thank you.
Actually, kind of similar comments, two comments. So one is related to physics. So you have done a pretty good job, but I'm still young and learn not too much physics, frankly. And so I just want to say that just beware. Just don't throw the physical concept. Just don't throw the jargons that you just learn about, not learn about. Just don't throw those terms around without actually understanding it. I saw a lot of different cases. You are actually, from what I understand, there are some mistakes in your presentations or in your physical concept. Okay, and so just make sure you find the right reference and then just understand all these concepts. And the second one is about, again, communication. So I know you work really hard on this research, the competition and also the experiments. And you know every details and in your bones, right? But remember, we juries, the one decide your fates, is the first time to listen to your talk. So don't explain all the unnecessary details. Now, you don't need to tell us how this equation becomes that equation. You don't have to tell us what the sign is. X cross y, x times y. You don't need to tell us that. Just tell us physics. And that's a long way to learn. I'm still learning. Okay. Okay. So just emphasize the physics. Okay. Okay. So any comments from jury? Okay. Let's conclude this physics fight. So you guys can have a dinner, right? Have a good sleep, right?